Hello everybody, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman Gupta, just welcoming you all to my amazing video. And in this video, what we're going to do is we're going to prove this integral equal to this thing. And I have written here that Euler's reflection formula. This is gamma of z times gamma of 1 minus z equals pi over sine times sine of pi times z, where z is between 1 and 0. Let me tell you something about it. So this is Euler's reflection formula, right? And we can prove this through a number of ways actually. Even I have done, but I haven't published yet. But yeah, if you want, I can publish a video in which I can just directly prove this one, right? But I thought that actually I got this integral from a book, and I thought that why this equals this one. Actually, that book just used this as an standard integral, right? But I thought I need to prove this down because I don't want a standard integral to just memorize everywhere, right? I have to know why this equals that. So I just worked upon it, and it took a lot of time to be proven, but it's all right. I took a lot of time, but I'm here with you all, and I'm just going to prove it down for you. This is quite easy to prove, but this integral is it's good. So I think it's gonna take a lot of time. So instead of wasting our time, let's move on to our video. Okay. So basically we have to integrate this integrand, right? X to the n minus 1 over 1 plus x. Before moving on to that, why not playing with Fourier series? And if you are following my videos, like my past videos, so you must have an idea about what are Fourier series. Or if you don't, let me tell you something. So Fourier series representation, I will not go that much deep, but yeah, I will just tell you something like this. It is a representation of f of x, that is a naught over 2 plus the sum as n goes from 1 to infinity of a sub n cosine of nx plus the infinite sum as n goes from 1 to infinity of b sub n sine of nx, where x belongs to an interval from negative L to L. So for our case, I'm just gonna take, this is Fourier series representation actually, right? And I'll tell you how to calculate an, a naught and bn respectively, right? Okay, so before that, let me take my function. So I'm just gonna assume my function as cosine of ax, and that is x belongs to from negative pi to pi. So this is my L, actually this is L, and this is my f of x. So on the behalf of these two things, I'm just going to calculate a sub n, actually a sub n and a naught. Actually, why we cannot evaluate this, because, okay, let me tell you. So basically, a naught is 1 over pi integral from negative L to L. This is your limits, okay? Like I have my limits from negative pi to pi, right? But I'm not taking that. I'm taking an standard, like for this one, an standard Fourier series representation, right? So it's f of x dx, and then a sub n is 1 over pi integral from negative L to L of f of x times cosine of, let's take not n actually, because let's take k instead. Well, it's just index variable, so it's not gonna bother us anymore, right? Because I'm gonna use n later, so I don't want you to be confused, that's why. So yeah, so this is cosine of ax dx, and bn is 1 over pi integral from negative L to L of f of x times sine of kx dx. So if you look closely, our f of x is it's an even function, right? So if you plug an even function here, and if you look at this function, so eventually this becomes odd because of this sine function, right? So if you if you are integrating this from negative pi to pi, or any negative L to L, so eventually that's going to be 0. It means this sum is 0, right? So that's why I'm just going to take this much amount of part for our function and our limits. Let's just dive into it. So for our case, like I'm just going to calculate for this case, right? So a naught is 1 over pi from integral from negative pi to pi. Our f of x is cosine of ax dx. So when you integrate this, this becomes 1 over pi integral from negative pi to pi. Oh, not actually, let's integrate it. So this becomes 1 over a times sine of ax evaluated from negative pi to pi. Okay, I hope you can integrate this, right? So this becomes a naught equals when you plug sine a pi minus sine of minus a pi over a pi. So you know that sine of negative is negative of sine, right? So that becomes sine of a pi, and negative times negative becomes positive, sine of a pi over a pi. So that's going to give us a naught equals to sine of a pi over a pi. So this is our a naught, right? Right? Okay. Let me just write down here, or I should erase this stuff. This is how you calculate for a, and like I have used this formula, right? So I'm not talking about the upper case, but I'm talking about my case, right? So a naught comes out to be 2 times sine of a pi over a pi. And now we are going to calculate for a sub n, right? Sorry, not a sub n, but a sub k. So, okay. So, from looking at the previous formula that I have written, a sub k equals from 1 over pi integral from negative pi to pi of f of x, that is cosine of ax times cosine of kx dx. So for this integrand, we are going to use a formula that is cosine of a times cosine of b equals cosine of a plus b plus cosine of a minus b. So for our case, a is like the capital A is small ax and the b is k pi. So cosine of a x times cosine of kx, it's not actually pi but it's x, sorry. So if you calculate this, so this becomes 1 over 2 cosine of ax plus kx plus cosine of ax minus kx, right? So yeah, and if you if you solve this, so this becomes 1 over 2, and you have to just take x common outside like this, a plus k times x and plus cosine of a minus k x. Yeah, this is how it's done, right? Okay, so now we are going to integrate this integrand instead of this one, right? So this becomes a sub k equals 1 over pi and times 1 over 2, that is, I can write it as 1 over 2 pi and integral from negative pi to pi of this integrand, that is cosine of a plus k times x and plus cosine of a minus k times x dx. Okay, and now we are going to integrate this one. Okay. So let's do this on that board only. So for instance, let me write this down here. And like you can just solve it on your own, I think. And if you don't, I'm here to explain all the stuffs. Don't worry. So yeah, this is what we have to integrate, right? Okay. So, yep, a sub k equals 1 over 2 pi. When you integrate this one, so this is a constant, so that would be divided outside the sine function, because when you integrate this, eventually that's going to be sine of a plus k whole times x, and again in the divide with a plus k, because that's a constant. You can integrate by your own, but I'm just telling you all the stuffs. So that's gonna be a plus k times x over a plus k and plus sine of a minus k times x over a minus k, evaluated from negative pi to pi. So a sub k becomes 1 over 2 pi. Okay, so when you plug the limits, so that's gonna be again like we did in the evaluation of a naught. Like what I'm talking about, when you plug sine of pi minus sine of minus pi, so that's gonna be 2 sine of pi. So that's what I'm just gonna directly write it as, when you plug these two things inside this, so that's gonna be 2 times sine of a plus k times pi over a plus k and plus 2 times sine of a minus k times pi over a minus k, right? So that's a direct approach you can do. You can think of it. You don't need to write all the steps. Okay, and now these two are getting cancelled out each other. So a sub k becomes 1 over pi times let's just multiply these two things along with each other inside the denominator, and to neutralize them, let's multiply a minus k here and a plus k here. So that's gonna give us a minus k sine of a pi plus k pi. I'm just gonna expand this, that's why I've written, like I have multiplied this pi inside this small parenthesis, right? And that again a plus k sine of a pi minus k pi, and over a plus k times a minus k is a square minus k square, right? So, and now we are going to expand these two things and we'll do something from that. So for that, let me just erase this one also, and let me just write down what our a naught here, that is 2 times sine of a pi over a pi. Okay, so wait a second guys, let me just check everything is recording. Yeah, okay, so now let's expand them. So how are we gonna do that? I hope you know. Let me just write down the formula. Sine of a plus b equals sine of a cosine of b plus cosine of a sine of b, and similarly sine of a minus b becomes sine of a cosine of b minus cosine of a sine of b, right? So that's what we are going to use, because if you just have a look at our case. So here in both the cases, A is A pi and B is K pi. So on the behalf of that, we are going to expand this one and this one also. Let's do that. So A sub k is 1 over pi and times A minus k. When you expand this, so I'm just going to write down after expansion what it's going to give us. So that's going to give us sine of A pi cosine of K pi plus sine of K pi cosine of K pi, then plus A plus K times, that's going to give us sine of A pi cosine of K pi minus sine of K pi cosine of K pi. So yeah, this is what we are getting. And now we are going to multiply this A minus K into this one and this A plus K into this one. Let's see what we get. So A sub K is 1 over pi. When you multiply A with this first term, so that's going to give us A times sine of A pi cosine of K pi. When you multiply A with the second term, so that's going to give us A times sine of K pi cosine of K pi, and now multiply minus K with both the terms respectively. So that's going to give us minus K times sine of A pi cosine of K pi, and then minus sine of K pi cosine of K pi. So this was your first we have evaluated this one, and now looking for this one. Let me just cover it, and then plus A times sine of A pi cosine of K pi minus A times sine of K pi cosine of A pi, and then plus K times sine of A pi cosine of A pi, and then minus K times sine of A pi and cosine of A pi. So yeah, successfully we did that, and now we are going to cancel some terms. Let me just have a look at all the terms that are being cancelled out. If you look closely, minus K sine of A pi plus K sine of A pi cosine of K pi, yeah, this one and this one getting cancelled out, and next A sine of K pi cosine of A pi plus, so yeah, this one and this one getting cancelled out. So eventually that's, and rest of the terms will be added together with 2 times. So eventually that's going to give us 2. Yeah, these two things are getting added. So 2A sine of A pi cosine of K pi, and then yeah, these two things are getting added. So minus 2K sine of K pi cosine of K pi, and don't forget we had A plus A square minus actually K square, right? I missed that, but yeah, I got that to know. So here you can just A square minus K square, you can write it down, right? And here also. So yeah, this is what it is all be like. This one comes out to be that, right? Okay, and now let's just do something more in this to simplify this further. Or maybe you can think of, okay. Yeah. So yeah, now we are going to modify this one because it's still looking free. So A sub k is 1 over pi and 2 is yeah, or maybe let's just leave it. Well, a was a constant at from the beginning, right? When we began our journey from Fourier series, so a was a constant. It was nothing, like we don't have any idea, but we have an idea about k. So if k is an integer, so sine of k pi is 0. Let me just write down here firstly. If k is an integer, then sine of k pi is 0 and cosine of k pi is minus 1 to the k. You have to note it down. So if you look closely, sine of k pi, this term is eventually getting 0, and in this term cosine of k pi is negative 1 to the k. So let's just do that here. So our a sub k finally becomes 2 times a times sine of a pi times negative 1 to the k over pi times a square minus a square. So this is your a sub k evaluates to, and we had a naught. So let's just construct our Fourier series as earlier we did that. So cosine of ax is a naught by 2. Keep remember that. So by 2 it means 2 and 2 getting cancelled out. So eventually we're gonna have sine of a pi over a pi and plus, yeah, so plus this one, the sum as k goes from 1 to infinity of this big term along with the multiplication of this term, right? So 2 times a times sine of a pi minus 1 to the k over pi times a square minus a square and cosine of ax. Okay, and if you look closely, then 2a sine of a pi and along with pi, these are the terms which are independent of k, so we can just pull them out. Or maybe let's not pull 2a actually, but let's pull sine a pi over pi. So cosine of ax becomes sine of a pi over pi and plus sine of a pi over pi times the infinite series as k equals 1 to infinity of 2 times a times negative 1 to the k over a square minus k square. Okay, let's just erase this stuff, and finally we're going to write down our result. So okay, again cosine of x, and since x belongs to negative pi to pi, so we can consider x equals 0. So when you plug x equals 0 here, so that's going to give us 1 because cosine of 0 is 1, and again this one becomes 1 also. So finally we're going to have at x equals 1 equals sine of a pi over a pi plus sine of a pi over a pi times the infinite series as at k goes from 1 to infinity of 2 times a times negative 1 to the k over a square minus k square. Okay, and now just take common these two terms and neutralize them. Like this becomes wait a second. Oh, I'm sorry, there isn't a in denominator actually, and here it was a. So yeah, please just correct them down, guys. Okay, so when you take sine of a pi over pi common, so this becomes 1 over pi times the sum as k goes from 1 to infinity of 2a times negative 1 to the k over a square minus x square. So let's just multiply and divide with this term. So finally we are going to have, like, you have to note this result down that I'm going to write down here. So 1 over a plus the sum as k goes from 1 to infinity of 2a times negative 1 to the k over a square minus k square is pi over sine of a pi. So this is what we have to do from Fourier series. This is what we need to we need to prove this sum. And next we are going to deal with our integral, because in this integral we are going to use this sum, and that's eventually going to give us that this integral equals this. So yeah, this is really exciting. So I'm just going to write this down. So 1 over a plus the sum as k goes from 1 to infinity of 2a times negative 1 to the k over a square minus k square is pi over sine of a pi. Yep. Okay. So finally we have done a lot of work, and now we're going to deal with our integral directly, because we don't need any kind of extra effort to prove this one. Okay. So let's consider our integral. So I'm just taking that integral as I integral from 0 to infinity of x to the n minus 1 over 1 plus x dx. Okay. So I'm just going to write this down in two integrals, that is from 0 to 1 of x to the n minus 1 over 1 plus x dx, and plus from 1 to infinity of x to the n minus 1 over 1 plus x dx. Because when you combine these two integrals with each other, so eventually that's going to give us from 0 to infinity, right? So I'm taking in consideration of this integral. So when you replace x with 1 over u, so limit's gonna give us infinity becomes 0 and 1 becomes 1. So dx is negative 1 over u squared du. So that's gonna give us integral from 1 to 0 of x becomes 1 over u. So 1 over u to the n minus 1 over 1 plus 1 over u and negative 1 over u squared du. So negative is going to help us to just flip the bounds of this integral. So that becomes from 0 to 1, and this becomes so this becomes 1 over u to the n minus 1, right? Or maybe let me write it down something like this. 1 over u to the n minus 1, and this becomes u over 1 plus u, and we had 1 over u squared earlier. So 1 u getting cancelled out, and I'm just going to multiply this u with this one, right? So that's gonna give us integral from 0 to 1 of 1 over u to the n times 1 plus u du. So that's eventually going to give us 0 to 1 of u to the negative n over 1 plus u du. And since, wait a second, and since that integral is that's a definite integral, right? So we can just change this variable with x. We cannot do in indefinite integrals, but we can do in definite integrals. So finally we are going to have x to the negative n over 1 plus x dx. So yeah, like this integral comes out to with this eventually after solving all the stuffs. So I'm just going to erase all the stuffs that I did here, and I'm just going to use the this one only, right? Okay. So I can write I as integral from 0 to 1, this one, x to the n minus 1 over 1 plus x dx, and plus integral from 0 to 1. I'm not writing this one, but instead this one, because they both are equal, x to the minus n over 1 plus x dx. Since bounds are same, variables are same, so we can combine them both. So integral from 0 to 1, x to the n minus 1 plus x to the minus n over 1 plus x dx. And from now onwards, we are going to introduce something. I hope you have an idea about 1 over 1 plus x is infinite series as n goes from 0 to infinity of x to the n. So that's gonna give us 1 over 1 minus, actually it's minus, not plus, 1 minus of minus x. Keep remember that 1 minus of minus x, it means 1 over 1 plus x. So I'm just gonna replace this with this infinite sum that's gonna come out. So this becomes n goes from 0 to infinity of negative 1 to the n times x to the n. So yeah, you can just think of it, right? From this one we did that, and this is just an infinite geometric series, right? So let's replace 1 over 1 plus x with this infinite series inside our integral. So I becomes integral from 0 to 1 of x to the n minus 1 plus x to the minus n, and times the infinite series as n goes from 0 to infinity of negative 1 to the n times x to the n dx. Since these two things are independent of the integral, so they're gonna just come out as a constant. Infinite sum as n goes from 0 to infinity of negative 1 to the n times integral from 0 to 1 x to the n times x to the n minus 1. Oh, wait a second. No. Oh, sorry. Don't take n, but take k. Don't get messed up. Sorry. Actually, I'm really sorry. Yeah, this is k. Okay. Please just correct it down. Please don't get messed up. This n is different and this one is different. Okay, yeah. Okay, yeah. Everything is fine. Okay. So, yeah. So x to the k times x to the n minus 1, it becomes x to the n plus k minus 1, right? When you just multiply these two terms. And x to the k times x to the minus n, x to the k minus n dx. When you integrate this, it's really basic integral. So that's gonna give us the series as n goes from 0 to infinity of negative 1 to the k. Sorry, again, I'm really sorry. Okay, yeah. The infinite series from k equals 0 to infinity of negative 1 to the k. When you integrate this, so that's gonna give us x to the n plus k over n plus k plus x to the k minus n plus 1 over k minus n plus 1 from 0 to 1. So when you integrate this finally after just putting all the bounds, so that's going to eventually gives us the infinite series as k equals 0 to infinity of negative 1 to the k times 1 over n plus k plus 1 over k plus 1 minus n. And now we are just going to use this one to just convert that into this one. That's our task. Okay, let's just move it. Okay, so I'm just taking the consideration of this infinite sum. So I'm just going to expand them actually. Yeah. So that's gonna comes out to be when you plug k equals 0, so that becomes 1 over n and 1 over k plus 1. Oh, sorry, k equals 0, right? So 1 minus n. And when you plug k equals 1, so that's gonna be a negative. So just remember that negative of, when you plug k equals 1 here, so that's gonna give us n plus 1, 1 over n plus 1, and here k, it's gonna be 1 over 2 minus n, and this one becomes 1 over n plus 2 plus 1 over 3 minus n minus, let me write the next term only, 1 over n plus 3 and minus, plus actually 1 over 4 minus n and plus dot 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 to infinity. Don't just forget about the alternative plus and minus, right? Okay, let's let's take this 1 over n like outside and considering this two things. So if I'm taking negative common, so that's gonna give me 1 over n plus 1, and if I want to make positive here, because if I'm taking negative here from here, so that should be negative, right? But if I'm taking positive, so I have to just take the negative inside the denominator, so that's gonna just flip the order, that become 1 over n minus 1. I hope you understand it. This is very important to understand, and rest of the things will be like automatically do like this, right? Let me tell you something about this. And the next term is, okay, so when you take this one, 1 over n plus 2, and when you expand this, so that's gonna give us minus, like here, minus of 1 over 2 minus n. So I'm just, if I'm multiplying, if I want it to be positive, so the order of the denominator should be reversed, and that's gonna give us plus 1 over n minus 2, and again minus, alternative, plus minus, and that's just goes up to infinity. Yeah, you have to think like this, you have to think here, because it's observation, right? Okay, so now we can just generalize it, and that's gonna give us 1 over n plus the infinite series as k equals 1 to infinity actually, of minus 1 to the k of 1 over n plus k plus 1 over n minus k. So let's take a look at here, minus 1 to the k, so that becomes 2n over n square minus k square. So yeah, this becomes 1 over n plus the infinite sum as k equals 1 to infinity of 2n minus 1 to the k over n square minus k square. This is our I, right? And now maybe you can relate it with this that we have proved earlier. Because when you plug a equals n, this is exactly what it is. Let me just write down on that board. So like our I comes out to be, let me tell you, we have with the help of Fourier series, we have proved earlier that 1 over a plus the infinite sum as k equals 1 to infinity of 2 times a times negative 1 to the k over a square minus k square was equals pi over sine of a times pi. Let's replace a with n. So this becomes 1 over n plus the infinite sum as k equals 1 to infinity of 2n minus 1 to the k over n squared minus k squared. That should be equal to pi over sine of n times pi. right? And if you look closely, then this is the same result that we have concluded so far with our target integral. It means that I equals 1 over n plus the infinite sum. I'm just writing this down again. Infinity of k equals 1 to infinity of 2n times negative 1 to the k over n squared minus k squared. Right? This was our I. This was our I. And these two things are same. So that basically says I equals pi over sine times n pi. Hence proved. Wasn't it so much cool? I just want to write down here this big stuff. Wasn't it too cool, guys? Wow. So we have proved that integral from 0 to infinity of x to the n minus 1 over 1 plus x dx equals pi over sine of n pi. This was all about it. Wasn't it so much cool? Because I had a lot of fun in proving this down. That's how mathematics is all about, dude. It's when you just dive into it, it feels like heaven. But still, we have to do a lot of work, and yeah, that was very good. I really loved proving this. And if you got to know anything, not a lot of things, but anything, thank you so much. Thank you so much. You got to know anything from my video. And yeah, stay tuned and please be subscribed, because I will get a lot of things for you guys. Just I need your support. Okay, then thank you so much. Bye. And just take a look at this view, especially that central view. That's really amazing. Actually, let me tell you something. I was wondering how it's really done. Like, I don't have any kind of proof. I have checked a lot of webs, I have checked a lot of things, but I never got something. But today I got something, and this is all about. This is everything what I got for you. Thank you so much, guys. Stay tuned.